All right, today we are cracking open one of the most powerful problem-solving techniques ever devised. This is the stuff that's used to control aircraft, price financial assets, even sequence DNA. But you know what? The secret to understanding it is hidden inside a dilemma that's probably a lot more familiar to you.
So, picture this. You're on the job hunt, and every single week a new job offer lands in your inbox. Now you can either accept it and start making that money, or you can say no, collect some unemployment benefits, and just hope for a better offer next week. So how do you decide? When do you stop waiting and take the plunge? This isn't just a random thought experiment. It is the key that unlocks the whole powerful concept we're talking about today.
The choice really boils down to this classic trade-off. On one side, you've got what's called the stopping value. That's the guaranteed cash you get if you accept the offer on the table. It's a sure thing. But on the other side, you've got the continuation value. This is the value of waiting. You get your unemployment check for now, plus the possibility of a way better offer down the road. So the big question is, how do you weigh a certainty today against just a possibility tomorrow?
Now, your first instinct, like most people's, is probably to start from today and try to map out every possible future. You could get a great offer next week, or a terrible one, or a kind of okay one the week after that, and it gets complicated really, really fast. But what if that's completely the wrong way to look at it?
That's right, the secret is a technique called backward induction. To solve the problem of the future, you don't stare forward into this fog of uncertainty. You go all the way to the very end, where things are simplest, and you work your way back to today. Let's just imagine your job search has a hard deadline, say 2 weeks. On that very last day, in week 2, your decision is incredibly simple. You get an offer, you compare it to your unemployment benefit, and you take whichever one is higher. Why? Because there is no next week. There's no more continuation value. The decision is totally clean and self-contained, easy.
And this is where the magic happens. Because you know exactly what you would do in week 2, and you can calculate the expected value of that final week, you can now solve for week 1. You can precisely figure out the continuation value for week 1 by weighing the offer you have right now against the known, calculated value of waiting 1 more week. See what happened? You just turned a complex, scary problem into a simple 2-step calculation.
This process, solving the end first, then the second to last step, then the third to last, and so on, that's the core idea. You're not trying to solve one giant, terrifying problem. You're solving a chain of small, manageable ones where the solution to each step becomes a known, concrete value for the step right before it. And this amazing technique has a name. It's called dynamic programming. It's this brilliant optimization method that's all about a divide-and-conquer strategy. You break a problem down into these overlapping subproblems, you solve each tiny subproblem optimally, and then you use those little solutions to build your way up to the optimal solution for the original, massive problem. This is all possible because of a core idea called Bellman's principle of optimality. Think of it this way. If you've mapped out the absolute best route from New York to Los Angeles, and that route happens to go through Chicago, well then the Chicago to Los Angeles part of your route has to be the best possible route from Chicago to LA. It just has to be, right? If it weren't, you could just swap it out for a better Chicago to LA path, and your whole trip would get better. Dynamic programming leans entirely on this simple yet super powerful logic.
Okay, so the theory is really elegant, I get it. But how does this actually work in the real world? When a programmer sits down to write the code, they've generally got 2 main ways to tackle a dynamic programming problem. These 2 strategies are called tabulation and memoization, and they're really just 2 sides of the same coin. Tabulation is the bottom-up approach. It's exhaustive. It starts with the smallest possible pieces of the problem and builds up, solving every single one along the way. Think of it like filling out a spreadsheet, cell by cell, until you get to the final answer. Memoization, on the other hand, is the top-down approach. It's more targeted. It starts with the big main problem and breaks it down, but, and this is the key, it only solves a subproblem when it absolutely has to, and then it remembers that answer in case it needs it again. So tabulation is comprehensive and usually more efficient, while memoization can be more intuitive to write and avoid solving problems you don't end up needing.
Here's a simple way to think about it. Tabulation is like trying to solve a maze by starting at the entrance and methodically figuring out the best path to every single intersection in the entire maze. It's exhaustive, and it guarantees you have all the information, even for parts of the maze you might never actually go through.
Memoization, though, is like starting at the maze's exit and working your way backward to the entrance. You only explore the paths that could possibly lead to your goal, and as you figure out the best way from a certain spot, you put up a little sticky note, a little memo, So if you ever find yourself back there, you already know the answer. It just trims away all the unnecessary work. So why does any of this matter? I mean, it sounds like a lot of work for a job search problem you could probably figure out on the back of a napkin. The reason is scale. Dynamic programming isn't for small puzzles. It's for problems so massive that trying to solve them any other way would be, and I mean this, literally impossible.
Let's consider a book retailer trying to manage their inventory. Let's say they have 100 different books, and for each of those books, they can choose to keep anywhere from 0 to 10 copies in stock, while the number of possible inventory combinations they could have is 11 to the power of 100.
And that number? It's just astronomical. It is way, way bigger than the estimated number of atoms in the entire known universe. So trying to use brute force, checking every single one of those options to find the best one, it's not just impractical, it is fundamentally impossible. But with dynamic programming, you can actually find the optimal solution.
And this power is used everywhere. From the AI that runs robotics to the algorithms that sequence our DNA, it's in finance, pricing complex assets, in logistics, routing shipping containers and controlling aircraft. Governments use it to model economic policy. Tech companies use it to power the recommender systems that tell you what to watch or what to buy next. It is this quiet powerhouse running so much of our modern world.
So the next time you face a really complex, daunting decision, whether it's in your career, your finances, or just planning a complicated project, remember this core lesson. The secret isn't always to just charge forward into the unknown. Sometimes the clearest path is found by starting at the end and working your way back. So what's a big problem in your world that you could start solving today, one tiny piece at a time?